All right, we're almost done with our video lectures on energy analysis. Let's do some problems or start setting them up. Energy analysis, Form 1. The work, mechanical work from all forces causes a change in kinetic energy on that object. Okay. Again, this is a heads up. We're not talking about how jiggling motion can turn into mechanical work. We'll get to that with thermodynamics. We'll layer that on. Okay, we could talk about if jiggling motion causes a movement, then ultimately it's from, say, gas hitting a piston and expanding it. So ultimately there are forces involved, and we could just call it work from jiggling motion or change in energy from jiggling motion, thermal, etc. This is often called the mechanical work energy theorem. The work from non-conservative is equal to change in mechanical energy. We can turn this into this form, and this is the form that we often use. Energy mechanical is defined as kinetic energy, all types kinetic, this all type of potential energy. So there's our toolbox start. I recommend starting there, filling it in, looking at what your earlier state, your later state in between is. Definitions, 1 FMV squared. Change of potential is the negative work from that associated kinetic conservative force. MGH, where you got to set H equal to 0, 1/2 KS squared or X squared. Equilibrium is usually 0. The definition of work you've got there. This is your toolbox for energy analysis. Work in the integral form, again, is between 2 points. Force, cosine of the angle between the force and the path, and the distance along the path is how we can look at that. All right, so intuitively, let's apply this. We talked last time, normal force. You might be surprised to realize that the normal force can do positive work. It can do negative work. It can do zero work, right? So as an object goes up, the normal force is up and the motion is up. Whoa. As I go down, the normal force is up, but the path is down. They're opposite, negative. If I go sideways, the normal force is up, but the path is perpendicular and there's no work. That's the only thinking that you need, and you can see that all works. So be careful. Friction. Friction can do positive work, negative work, which is what we often think of it, or zero work. Tension. Tension can have positive work if you're pulling it in the direction it's moving. It can do negative work if you're pulling back as it moves forward or whatever. You're pulling opposite direction. Or if the tension is perpendicular to the motion, then again, it's not doing any work. This is true, of course, of gravity, which we usually turn into and think of in terms of potential energy of gravity. Gravity can do positive work, negative work, or zero. So gravity doing positive work means that gravity is in the direction of motion. Gravity doing negative work means that gravity is in the direction opposite the motion. Gravity down, motion up. Gravity doing negative work. Change of potential energy going up. And this is negative, this is positive. Gravity doing positive work. Potential energy going down. When you exercise, if you lift weights, there's a lot of weight, as I'm pushing up, I'm pushing in the direction it's moving. That's called a positive rep because I'm doing positive work. Now I push up so that it doesn't speed up. I push up and lower it slowly. I push up as it moves down. I'm doing negative work. That's called a negative rep. A positive rep, a negative rep. Okay. If I push on something and the thing's not moving, I'm not giving it or energy and I'm not taking energy away, so I'm not actually doing work. I may be expending energy, but we're talking about the interaction that gives or takes away energy from the object. So I can push all day, I'm not doing any work. Okay, there's some good ideas. And spring, as we saw last time, can be positive, negative, or zero. So you really just have to look. So the key is see and draw the forces and the path, and the angle between the forces and the path is what's important. Are you with the motion, opposite the motion, perpendicular, or is there a component? Here's a problem, real quick. These get pretty simple once you get the groove. Object starts out with some velocity v1, then it stops. There's some coefficient of kinetic friction here. What can I find out? How would I set that up? Well, whatever's being asked, I can just start here. I would start state 1, state 2, work non-conservative from 1 to 2 is equal to the energy at 2 minus the energy at 1. And then I layer in the details. At 1, what have I got? Let's see, at 1, I've got 1/2 mass times v1 squared. Now I haven't said where h equals 0. It could be here, it could be here. But since h isn't changing, why put it in? So no need for it at all. And energy at 2. Well, it stops and it hasn't changed height. So 0. No mechanical energy, no bulk motion energy. So I can right away figure out, without doing anything, how much work was done from 1 to 2. It's this much work. So you can get your work energy theorem to give you the answer over here. Or you can look at the definition if there's something else that you want. So something else that I want, well, what's the definition of work? What's doing work here? I've got, well, what did I say? Draw the forces. So what are the forces? I've got gravity, mg. The work due to gravity is handled by the potential energy. We just moved it to the other side. I've got the normal force. How much work from the normal force? Now that's non-conservative. Normal force non-conservative. Gravity conservative. 0. Normal force is perpendicular, so you don't need any work from the normal force. And then I've got, of course, friction. And in this case, when it's sliding, friction is slowing it down and stopping. So Fk is equal to mu k. And in this case, not always, you know to be careful. In this case, you can clearly see that n is balanced by mg. So I've got that. Okay, cool. I can also see that the path here, the path is forward here, that way. They're opposite. So clearly friction is doing negative work. It's going to be a negative force of friction times the distance traveled. In this case, I'll just call that delta x. And then in place of friction, I can go negative mu k mg delta x is equal, and then I can solve for whatever I want. So you simply fill in the details. All right, cool. So that's one case, but every case can be different. So you just take a look at each thing and see what you've got. This same result can be obtained through kinematics and force analysis, right? But be careful, if you're taking an exam and they're wanting you to use energy analysis, you're going to use energy analysis. On my exams, I say you must use momentum and energy analysis because that's what you're training. It's good stuff. Okay, cool. How about another problem? Oh, the other point I want to make here. So, friction takes the kinetic energy away. Where does it go? Where does that energy go? It goes somewhere, right? And so, of course, it goes into jiggling energy. It might make some sound. Certainly, the surfaces get warm. So this surface gets warmer, and the surface of A gets warmer. So you could say, well, you didn't really take it all away from A because you made it warmer. That's right. That's a bookkeeping thing. Some books will say, for friction, they'll use this term delta E thermal or something like that. I just say, that's the interaction friction. It does slow you down. You can calculate it based on the definition of work for that. And you know where it goes. It goes into the warming of the surfaces, the jiggling energy, if you will. So I highly recommend treating the work due to friction as just friction as a force. Use the standard definition here. Take every non-conservative force and address it that way. Let's take a look at this case. So now if my object of interest is, say, B, and you're pulling it with this constant force F, or 88 newtons. And I might ask the question, hey, if you start from rest, how far do you have to go in order for the velocity 2 to be 11 meters per second, which is about 22 miles an hour, right? Which is the top speed of the fastest humans. Okay, so, gosh, what do I do? What do I do? Oh, I'm going to use kinematics because I'm used to that. I'm going to use force analysis because I'm used to that. No, no, no. We're going to train and use this great tool. So we're going to start with a framework. We're going to go, hey, work non-conservative, 1 to 2 is equal to E2 minus E1. Now fill in the details. All right, energy at 1 is 0. Oh, wait a minute. I have to decide what I'm looking at. So if these move as a unit, one way of doing this is to treat them as a whole unit. So there's lots of questions we could ask here. So we treat that as a whole unit. We've got a constant force. And it's going to move some. So let's do that first. All right. Starts at rest. No springs and no change in height. So E2 here is going to be 1/2 the mass of A plus the mass of B times V2 squared. That's it. Now you might ask, well, what about E is kinetic plus potential, all types. I've handled all that stuff. What about friction? So in here, I've got the work due to F plus the work due to friction. Now, if the friction is negligible, then that's nice. The work due to F, of course, is going to be positive because you're moving in the direction of motion. F, which is 88 newtons, times your delta X. And so if you want to know how far you're going to go, then there's your delta X, right? So in this case, don't make a big deal. You don't need to integrate this. It's just clearly going to be this. If you have negligible friction, happy day. If you don't, then the friction clearly is going to be this way. And it'll be kinetic for that whole thing. So then you're going to have minus the friction. And maybe you just want friction. Just put it in there. Times delta X, right? Any other non-conservative forces? No. Just put it in. Okay, let me just work with what I've got, factor it out, do the algebra, and you're good to go. Okay, so again, I would treat friction as a non-conservative force. Just put it in there like the rest and work with that form, and you're good. Now, another question is interesting. What about B? If I just look at B, so that's looking at the combined one. A and B, always good to note what you're doing, and then move on over here. So let's just look at B. I'm going to look at object B and say, hey, what's going on with B? Well, let me draw a little picture of B. B goes from 0, V1 equal to 0, to V2 over that same distance, delta X. I've got forces on it. I've got force of mg. I've got force of normal. They balance in this case, so I do know that the strengths are equal. In this case, you can see that. What else? Oh, the normal from what? The normal is actually from right here. This normal is occurring right there. There's a contact here with A, right? So it's different than the normal before, the normal from A. And there's a contact there. In fact, what makes it speed up? Ha! That's kind of cool. It's got to be the force of friction. But what kind of friction is that? Well, B is not sliding relative to A, so it's got to be static. Now, in general, that's it. If you're going as, if you're accelerating as rapidly as possible, then, and this is about to slide back relative to A, then you can use static max. Or Fs max, which that has an equation Us n, right? Otherwise, you just use that. Hey, what's this? Okay, let's do this real quick. See how we're doing here. Work non-conservative on A from 1 to 2 is E1, E2 minus E1 of A, or excuse me, of B. This is B, right? And then I look at that, and initially it starts at 0, so that's nice. And then afterwards, I'm going 1/2 mass of A, because I'm looking at it, V2 squared, still the 11 meters per second. And since I'm looking at it, this isn't doing any work, because it's perpendicular motion, and I don't have any change in height. This isn't doing any work. But the friction is, and the friction does the work of positive Fs delta x, doesn't it? Static friction is the thing increasing the speed. It's the force doing that. And yes, you can do all this with kinematics and force analysis because these are simpler problems that are ramping you up to use energy analysis in a more efficient way. How are we doing on time?
Good. 15 minutes.
Let's roll on and do a couple more examples. And all you have to do is slow it down and ask the right questions. Go slow to go fast, okay? So draw the forces, the path, the angles. Start with a template and just work in the details. So let's go over here. This one's a mess, right? And then I got a doozy for you. But just rely on the basics and take yourself deeper into what's going on. Suppose, you know, the old inclined plane, I got this incline, I got this hanging off the table, and this is some angle here. Now, you're going to start having some problems where there's multiple angles. So just because I wrote theta there doesn't mean it's the theta related to work. You have to see it. So just lay it out slowly, and you'll get there fastest. You can call this theta of the inclined plane, I, or whatever you want to do. I, there, whatever. All right, so now what's going on? Well, again, I can treat this as a system, or I can look at each object individually. I'm not going to do this all, but I'm going to show you that for B, if I just looked at B, what are the forces on B? Of course, there's mg, but I'm not going to treat the work definition, not going to use the work definition. I'm just going to look at the fact that B goes up delta H, right? So maybe I say H1 is 0, H2 is equal to theta, if I call that delta x sine theta, incline, something like that. So mg is handled by looking at potential energy change, right? All right, and then there's the normal force. Let's see, does the normal force do any work? Normal force, see the force, and see the path. They're perpendicular, so that doesn't do any work. What else is there? Well, there's possibly friction. If there's friction, it's kinetic friction, right? What's the work there? Well, it's going to be negative because it's opposite the motion, negative Fk, delta x. And what else? Oh, I've got tension. Oh man, what a mess. So lots of stuff. What's the work there? Positive T delta x. No angles, pretty nice. So the non-conservative work is done by this, and this, but that has a work equal to 0. Work normal is 0. This is handled by looking at the potential energy MGH. Okay. What else? A, we can look at A separately. Now, by the way, you may need to do a little quick force analysis to figure out Fk, because it's going to be mu Kn, and then n is related to the cosine mg cos theta, and if there's other forces, you may have to do that. Okay, so you may need to pull a little force analysis in there. A, what do I got? I got tension, T. And notice that this amount is the same as this amount. It might not be bad to just call that delta x. That's the same as that, or D, or something like that. You can call that D, and D. This goes up D, this goes down D. How much work is done? Negative TD by the tension. And then gravity, well, for gravity, I just look at mg, mg, positive mg over d, but we're not going to do that. We're going to use that as mgh. So again, the work for A, non-conservative, from 1 to 2, is energy of A at 2 minus energy of A at 1. This goes into the, here is potential energy. The tension is the only non-conservative force. Negative T times D. And then I've got some kinetic energy issues, so a lot of things could happen. And you just set it up and put it in depending on your problem. All right, let's do some more. Quick setup. Take a look at this one. Come on, here, redraw this. I don't want to go 45 degrees. Suppose I'm pushing this way. F. Well, again, see the force, see the path. The path is going to be here. Maybe. I mean, it could be going downwards. I could still push horizontally like that. And there's the force. So how much work do I do from that force? Well, the angle between this and this is F theta. Now, is that the same theta as this? You see the geometry, it is, in this case, but not always. So be careful, you know, you can have different angles. You just see it, that's the answer, it'll tell you. So how much is that work going to be? Well, it's going to be, if I go up, let me say I go up D here, and so then the work due to F is with the motion, positive, but only part of it, F cos theta D. And that's by definition, right? Definition of the work. You still have to put that all into work, all non-conservative, 1 to 2 is energy 2 minus energy 1, and just check out all the forces. Normal's not going to do any work. If there's friction, sorry, you got to put that in there too, and so on. Kinetic energy and potential energy changes in there, fine. Now one more here, and then maybe another. How are we doing on time?
23.
All right. Let me just throw this out, and then maybe I'll get another problem. So if now you pull at some angle here, so that this is F, this is the angle, I'll put the angle of F or something like that. If you still slide along that surface, you're going here. This angle is theta of the incline, but this can be very different. So, you know, professors can get a little tricky just to make sure you know what you're seeing and doing. The work here would be from F cosine of theta F times the D there. And so that's the angle relative to this, not that angle. So look carefully. We've got one more that we'll do, a little quick one, short one, and then we'll get into the final little bits.